Hi everyone, my name is Adi and I'll be your moderator today. Thank you so much for joining today's webinar on Bitemporality. Our speakers are subject matter experts on everything Bitemporality. Today we have Jeremy Taylor, Head of Product for XTDB, an open source database for solving complex problems with dynamic and temporal data. Before joining Juxt in 2019, Jeremy held a sales engineering position within IBM, working on e-commerce systems. For over a decade, Jeremy has been fascinated by relational and non-relational databases and is motivated by the promise of data abstractions that can improve developer productivity across domains with frequently evolving schemas. We also have James Anderson on the line. He's the engineering lead for XTDB. James has been working on XTDB since 2019. He's an experienced software engineer and has held leadership positions in companies ranging from an international investment bank to small startups. He writes Clojure, Java, and Kotlin, and has been responsible for wider software architecture, data engineering, and system administration. So without any further ado, Jeremy, the stage is yours.
Thank you. Hello. So welcome, good afternoon, good evening, good morning. So we at Juxt have been working on XTDB for the best part of 5 years. But this webinar really is a more abstract look in the round at one of the biggest pillars of the XTDB vision, which of course is bitemporality. So I won't mention XTDB much more, but just for anyone who doesn't have that context, that's where we are. So in today's session, I have a little agenda of things I wanted to cover, namely take you through why I think the state of the art, the way people commonly use databases is a bit flawed, and why I think it's necessary for your applications to think about time more routinely. Next, I want to talk about bitemporality itself, what does it actually mean, sort of decomplect or demystify that term. Next, I'll tell you about SQL 2011, which was a standard released to address some of these concerns and this gap in the SQL language for bitemporal functionality. And then I'll talk to you about the various challenges, whether you're trying to build a bitemporal system currently or thinking about it in the future. Be sure to follow along there. And then finally, I'd like to leave you with some tips, I guess, for how you can embrace bitemporality in your existing systems or in the future with technologies that exist today. Okay. So whenever I think about bitemporality, I think when I started working on XTDB, I jumped to this sort of vision of time travel. Like it's got a fun idea of going backwards and forwards in time and seeing things as they were or as they might be. But it's very sci-fi, and actually I think it's sort of the wrong mindset to have when coming into this. The sort of polar opposite of that is thinking about Plato's definition of time as the moving image of eternity. And I think it's a very powerful definition, which makes you question causality and whether time is even real. But this webinar isn't about that, and really it's not the right way to approach this topic. And instead, I think we should focus on the sort of the tangible, practical realities around us related to time. And in short, reality is messy. So when we talk about reality in terms of data, we're trying to model as best we can what we know about things. And when we're working in businesses with complex domains, we often find that the things that we need to do to capture the complexity of the business processes takes a while to encode and to get right. And so inevitably, systems evolve over time in conjunction with businesses giving feedback about different processes they would like to have in their software systems. And this has generally been the trend in software for a long time. But one of the things businesses do like is the ability to make changes and corrections, and for the software to adapt and mold to those evolved business processes and exceptions and those kinds of things. Kent Beck wrote a blog post recently, and in it he quotes, "We want what's recorded in the system to match the real world." And it's not just people within businesses who want that. It's actually people outside of the businesses, maybe industry regulators and auditors who actually mandate that or expect that of businesses. So if you can't make what's in your database match the reality of your business, then you're going to be leading yourself into a world of problems. Now, of course, reality genuinely is very messy. When I was putting together this webinar, sort of in the middle of that, even after we announced it, Kent Beck published this great blog post on redefining bitemporality in a term that he calls eventual business consistency, and I do recommend giving it a read. It's a sort of very good high-level view of what we're talking about today, although I want to get a lot more into the specific technical details. But yeah, suffice it to say, I had to refactor and reimagine what I was going to share and some of the narrative on the basis of this, because I think the way he frames things is absolutely great, and yeah, I'd encourage you to look at that. So yes, it is messy. One of the quotes he has in that article is, if what's in the system matches the real world as closely as possible, costs go down, customer satisfaction goes up, and we are able to scale further faster. So his real argument is to people that run businesses, so they're not really necessarily involved in IT, to try and justify why we need to bring in these extra concepts, why we need to think about time in this way, why we maybe need to spend extra effort early on in a project to cost scope out the temporal problem. And really the argument around efficiencies and cost savings, I think, is generally. So databases are obviously where people store data in general. So databases have been developed for the last 40, 50 years or so in various incarnations. But I think it's fair to say that most databases are, sorry, I think there's a connection issue. Most databases are grounded in the present. So when you change things inside of your database, it replaces the information with new information, and that sort of old version is lost. And that's the default mode of databases. And there are good reasons for this. So historically, databases were built for very small hard disks. And as a consequence, we have these languages, these database languages like SQL, which make it hard to remember or to forget particular information. And we have to sort of work harder in the application to program that in. And generally, these databases aren't designed to keep lots of history, which means you have to keep moving data out in order to keep performance as good as possible. So I actually went sort of further into this argument about SQL specifically in a presentation. So if you're interested in that, the presentation is called Update Considered Harmful, and I make the case that losing data is bad for business. And the reason is that essentially you don't know what is or isn't valuable to keep. So the default should be to keep things. So there's a bit more of a historical story there. But I want to move on to more specific topics. And an example is like looking at in a database that only models now, if you have a relation or a table, a set of customers, and you want to update or change a value in that table, that's great. You can do that with SQL. And what you can't do, though, is easily keep hold of the previous value. And so either the value is sort of lost forever and it's reclaimed by a sort of built-in garbage collector within the database, and the storage is reclaimed for future inserts. And if you're lucky, you might have a backup and a point-in-time recovery system, which also stores a copy of that, but it's basically inaccessible from the perspective of the language. And so from a developer's perspective, it's very hard to work with a system that's always changing if you actually need to be able to remember or recall the previous values. And there are many use cases for remembering, of course. And as developers, the obvious comparison is, would you develop code without version control? And that's essentially what we're doing when we're using these mutable databases or these update in place databases. So yeah, I think one very key argument to make is that for all the same reasons that you would want to use Git for version control, they basically apply for databases as well. So you want versioning. So the next question then is, how can we incorporate time and history into databases that operate with just now? So there are obviously ways people work around this. It's not the first time anyone's tried to solve this problem. One example of the language used to talk about this that I quite like, and there were some good threads about it last year in Hacker News, is about soft deletion. So this is the common problem in user-facing applications where, like, a user wants to make an edit to a document or a field, and rather than getting rid of the old data, you want to add a flag, a column on your table that just says deleted equals true, or deleted isn't null, and then in your query you can filter out for those deleted records, so you don't see them. And that way, when the user says, "Hey, help! I've made a mistake. I want to undo," that you can resurrect that record very easily. And there's also arguments around whether you want to be able to easily debug things. So soft deletion is quite a hot topic, and when this came up, I thought this is a great way of explaining bitemporality, at least at one level. And then I sort of went digging, and I saw the very first post about this on Hacker News was back in 2009. And so this is like a perennial debate about, is it a good idea? Isn't it a good idea? When is it justified to think about soft deletes ahead of time when you're building your application? And one of the comments in this article, The Trouble with Soft Delete, is they're basically saying just don't try and add soft delete unless you really need it. It's quite hard to do, so just figure it out later, basically. And there are obviously contrasting opinions, and someone here made a sort of another article where they've broken down the pros and cons of various approaches to soft delete. And I think essentially this is a way of describing a class of problems where there's a lot of confusion out there about the best way to do it. And I think this is a symptom of the fact that databases are operating in the now, and this is hard to model with existing technology. So to illustrate the problem more concretely, let's look at an example around pricing. So anyone who's ever built any kind of e-commerce system or any kind of maybe an inventory pricing system will have seen a table where you have a set of products and some prices. Now, if I want to update this table, I also can do so using whatever query language I have. But I'm essentially losing information every time I do it. And I want to walk you through this example to show you how I might go about preventing losing information naively if I was to simply add some fields. So the first one I might try is to add a created app. So this at least tells me when something was entered into the database. It's the most basic level of tracking the history. Of course, once I've changed the price, I'm not going to change the created app date there. So then I might have an updated app field, which is separate. And here you can see the banana changed in August, but it doesn't show me what the previous value was. So that's still not good enough to be able to really maintain history, although that metadata may be interesting. Next, we may have a version field, and we have some auto-incrementing ID, which acts as like a compound primary key. And yeah, here we can see that banana has two entries, £2 and £3 or dollars. And yeah, essentially this is like starting to hint at what may be an appropriate solution is for like absolute basic, don't lose any information. But really the state of the art for just sort of doing it yourself naively is probably to have a table of current prices and then have some historical table. So you can see the old banana prices piped off to the historical product prices table. And this approach sort of works. It makes things complex, like how your triggers work and at what point you should query the historical prices table and how you write the queries to join across them. These are not trivial queries to write, but it's doable. And a lot of databases end up with tables that look like this. And there is a name for this sort of pattern as well, which is system time temporal table. But strong mutation history or storing the mutation history like this is of course useful, but why is it useful? And the language I like to use is basis. Having a stable basis where you can say when things changed allows you to do repeated queries and get consistent results. For instance, if you have financial reports, you can actually calculate the report and put it on someone's desk and have it be the same outcome. So you're able to prove the calculation in that report. If you're talking to customers, you want to be able to answer them honestly about why their bill is wrong or why it needs adjustment. If you have complex application queries, you may actually find it easier to not have one huge 1,000-line SQL monster where you can decompose that and run it at multiple points in time, but against a stable historical time. And also for change detection, where if you have a table that's updating frequently, you maybe need to synchronize that with a search index or something like that, and you want to be able to say what's changed and replicate that out to the other system. So yeah, basically just storing the mutation history is a good idea. And from a developer perspective, it's of course great to have the ability to access the old versions and to be able to restore them. And when we're trying to solve bugs, it's generally easier to have access to old copies of the data if you don't have sufficient logging in place. But is mutation history enough to capture everything you might want to do? And I think generally the answer is no. Anyone that's worked with systems that offer time travel built in will eventually hit up against problems like I want to migrate data out of order, for instance, like I have a migration to a new system and I want to import some recent data, but then I also want to import the old data as like this late arriving bulk import. Or maybe the schema changes and I need to adjust the columns, but I can't do that on the old data. And if I try, I'm sort of mutating the past, which is the whole point of being immutable or not adjusting the history like that. And you want to be able to correct earlier versions. So if I have a version of a row that I know is wrong in the past, you want to annotate that somehow. So having some first-class means to do that is generally quite valuable. And then there's this broad idea of time travel where you want to run as of points in time. And if there's any use case in your application, like you're trying to preview the future, or you're trying to retest a scenario against some past data as the data came in, then time travel is an essential feature. And just looking at versions with created dates isn't enough. So then maybe the question is, who invariably needs history and time travel? Is it this esoteric thing that only some people need? Well, I think the use cases are completely cross-cutting. Every domain has some use cases to justify thinking about this or to treating the topic with some rigor. For instance, in Kent's article, he talked about customers moving and them informing the retailer about the address changes, saying things like, I forgot to tell you that I moved last year, you got last year's address change wrong, and I'm going to move next year. And those three quotes roughly align with the last three rows in that example there, where in 2021, I'm saying in 2020, my address changed, or the address changed. And in 2022, I'm saying in 2020, I changed it to the wrong address, like I turned a 4 into a 5, someone fat fingered the keyboard. And then in 2023, I'm saying in 2024, my address is going to change again to a different zip code. Equally, anyone that works with employees, where you're continually having these retroactive or post-active changes to records, saying someone's salary is increased or decreased, someone needs to book off holiday, or someone is available to work, an X number of days, or they have worked, and that needs to be billed against a particular client. That kind of problem is generally ubiquitous, and also maybe even beyond employees, you've got things like asset management, where you have like a room in a building that needs to be scheduled or booked with some equipment that needs to be booked, and the intervals for those bookings need to be immutable. You need to be able to say from and to, and make sure that things are available when they're supposed to be available. And I guess the more general statement is anyone who works with any kinds of calculations, so beyond just pure CRUD operations on top of your data, if you're actually needing to process that data and reliably come up with a calculation, and that calculation has all kinds of advanced domain logic, and maybe it's some clever SQL formulas, or you're pulling the data out into your application, you're saving it back down. But if you ever need to be able to answer a question to a regulator or to chief financial officer that says, this is what the value of the portfolio was as we thought it was at this point in time, then thinking in this way is basically unavoidable. And in industries in finance or insurance, yeah, this is very commonplace already. But what we found is that basically everyone rolls their own way of thinking about this and doing it, and they've all got their own language, because there's basically no very, very common standard that everyone follows. We think that's something which is why we're giving this webinar, right? We think it's an important topic. And then the final example, because it's something I feel quite compelled to talk about his the idea of the products and having prices and promotions and taxes and these sorts of things changing over time is really essential for any retailer to understand what their margin is, what it's going to be, and making sure that customer experience is correct, so that as someone's browsing the website, on Black Friday, that they're seeing the price that everyone's expecting it to be, and then these prices need to be agreed with the supply chain, the manufacturers, and because it's probably a large company, it probably is quite important that the pricing calculations are completely transparent if they are to get audited or what have you. So you can see you've got multiple versions of multiple things across multiple tables, and it gets very complicated without like a rigorous way of thinking about this. And so people build technologies to solve this, usually on an ad hoc approach. There's many projects that have like a library or an extension to an ORM, object relational mapping tool or library, which tries to solve this. We've seen many examples. And really the list goes on and on. Like many industries and use cases can benefit from having this first-class understanding of versioning. So with that, I'm just going to pause, take some water a second. How can we rigorously model historical versions of rows in the relational model? I think this is ultimately the question that is being asked when we consider versioning and history and time in a database. And when we've looked at this, the answer is always bitemporality, or at least that's at least the initial answer, because it's something which has been reflected on basically since the relational model was conceived. People started asking questions about, well, how does this set theory that is very good for querying things, how does it change, or how does it understand the idea of change in our systems? Because of course, at the time, disks were very limited. The focus was all about the query facilities and the indexing rather than the transactional model. And so bitemporality has always been sort of late arriving afterthought to the relational model. But people have been working on it for a very long time, and the big name in academia, the most sort of cited person, is Richard Snodgrass, who first was writing about it in 1988, and then he published a book in 1999 called Developing Time-Oriented Database Applications in SQL, which we'll talk about at some length. But yeah, essentially he had this vision for how to do it, which was a bit different to everything that had gone before it, and he had this very well-defined, well-delineated model that other people thought, hey, I can get on board with this. Whereas up until then, lots of wacky ideas for extending relations were out there, but nothing had caught on or convinced everyone it was viable. And in Richard's book, he talks about this insurance company in Denmark called Nykredit. They were at the time, and obviously still are, delivering insurance and things for the local market in Denmark, and they had some changes to regulations back in the 90s that prompted them to think about this problem of bitemporality. And so Richard's examples are sort of in collaboration with Nykredit and looking at solving their business problem, which was really around tracking the sale and receivership of property over that period in the 90s. So the data model is roughly this, where you have customers and you have properties, and then you have this join table called property ownership, which of course joins between them. But the idea is that a customer can own many properties, it could be a landlord, and we need to track in order to understand the mortgage liabilities to see who owned what and when, like very important questions to answer. And I actually had the fortune of going to visit Copenhagen a few months back and actually managed to find that building, which was quite a nice unexpected surprise. I didn't think it actually existed. But anyway, moving on. So the main sort of takeaway that the bitemporal model has, like if you remember nothing else, just like always record two timestamps along with your data. Of course, that's kind of what the name means, but it's the meaning of those particular types of times that are important. One is the timeline of when things actually happened, and the other is the timeline of when information was inserted into the system. So these are orthogonal dimensions, which should be thought about separately, although bitemporality, of course, is bringing them together. And this is another quote from Kent, where he says, the purpose of the two dates is to make sure that our system is eventually consistent with reality. So that is the bitemporal idea in a nutshell. To visualize that, there's a diagram here which shows system time where you're only ever appending to the end of time. You're never mutating what's gone before. And then valid time where you have this mutable notion of time, and you can put things into the past, the present, or the future. It's basically down to you as an application developer how you want to use it. So key property, system time is immutable. It provides auditability, and so we can go back in system time and say, what do we know at that point? Maybe more across more than just one table. In theory, the timestamp should be unique enough, with nanosecond precision, that we can say, what did the entire database know? So not just the state of a table, state of a row, but across the system. You can think of it as a system lifecycle. And as I said, this word basis, I think, is quite important. It leads naturally onto the idea of decision making, basis for making decisions. Obviously, companies thrive on making good decisions, not bad decisions, and understanding that what's happening in the future, what's going to happen in the future, is very important. So if you're going to think robustly about what might happen in the future based on information from the past, having system time to sort of lock down that projection is critical, really. Otherwise, you're making decisions that are hard to replicate and hard to debug, I suppose, for want of a better word. And so valid time is mutable. It's potentially meaningful to the application. You don't have to use valid time, but it's knowing it's there is like it's a feeling of safety. So much like soft deletes, to knowing you have a way to temporarily hide something, pretend it's deleted, and bring it back to life. It's very valuable. And really, you can think of it as a domain lifecycle of a record. So anyone who's worked with state machines knows there's always changes to the state machine, and you really need to model like a linear sequence of arbitrary states, and that's what valid time is. It's temporal versioning, using timestamps. So you can use that however you want to model domain lifecycles. Now, in terms of actual implementation, usually timestamps are treated as periods, and we have the valid time period and the system time period. And bitemporal data simply says that you have these periods, and the periods don't overlap, which we'll come to in a moment. So when you have, say, some pricing data, this example is from bitemporal.net, from a sort of data warehousing and analytics use case. But essentially, you can see they've got 4 columns. Now, I've just said you only need 2 timestamps, but there's some truth to the fact that ultimately you can generate from and to implicitly based on the earlier timestamp or the later timestamp. So as you insert new rows, you're sort of closing the interval or the period for the previous row. And what you end up with is these rectangles if you plot it in a 2-dimensional space. And the main rule, if there is one, is you don't have overlaps. If you have overlaps, the whole model breaks down. And whether you actually store 2, 3, or 4 timestamps in the table is basically a trade-off of performance. And if you store 4 timestamps, then you get faster read performance at the cost of some extra complexity during writes. So just be aware that that's a model. Also, the terminology here is wildly varied. System time and application time are used in the SQL 2011 specification. So if you download the ISO SQL document, it uses these terms. Snodgrass used valid time, so that's what I've been talking about. And I do think system time is a better word than transaction time. Ken Beck was using effective time and posting time. Anyone who's worked with event streaming systems like Kafka would probably recognize event time or ingestion time or log append time. These are other synonyms. But essentially, we're just talking about the same concepts, the time that data entered the system and the modeled time. And there are 2, well, let's look at this. So we have comparison of, on the left, we have application time, the history of things being modeled, underpinning user-facing features, modifying the past, present, and future, maintained by your app. On the right, system time. It's not about any of those things on the left. It's about history of changes to the database, auditing compliance, immutability, being append only. And then finally, it's something which should be maintained by the system. That's why it's called system time. And so as long as your use of time in your given application respects that, yeah, you may have some synonyms, but broadly they should be discrete functioning, and the 2 times should be orthogonal and roughly correlating with these features or capabilities, then you know you're onto a fairly vanilla model of bitemporality. So Richard, in his book, has these great SQL 92 examples of how to implement bitemporality from scratch using nothing but SQL. And so I'm just going to walk through those relatively quickly, but I do recommend looking at the book. It's freely available online to digest this at your own pace. So again, this is the data model. We've got customers, properties, and property ownership. And we see, first of all, that we define in SQL 3 tables. So we can see start and end dates for valid time and transaction time, as he calls it, or system time, in all 3 tables. And then some extra fields on those tables, of course, to model the actual data. So yeah, he's not using any built-in features of SQL. This is just all in user space. And on the right, we have these 2 assertions, which are check constraints that prevent us accidentally creating overlapping rectangles. In that diagram I showed you before, as I said, if any of those rectangles were to overlap, that'd be catastrophic. So this just makes sure that whatever we attempt to insert into these tables respects the fundamental constraint there. And essentially that's about bringing in the timestamps as part of the primary key. That's kind of what's going on here. So in this example, we have Eva Nielsen. She buys a flat on the 10th of January. So we insert this into the bitemporal diagram. You can see on the left, it goes up to 10th of January. And today is also happens to be the 10th of January. So the bottom left corner of the Eva rectangle is essentially now, assuming that we're in the past and we're reading a book in 1999. We can assume that that's just inserting data into the database, like not really reading too much into it. The arrows out from the boxes sort of indicate that this information is true forever. So until we assert some new information that replaces this version of the data, Eva will always be the owner as of the 10th of January. But of course, we find out some new information. Peter has bought the flat on the 15th of January. And what we're doing is closing off the previous information periods using this update statement. And we're saying that the new value is this. But actually that SQL that you see on screen there isn't what you actually have to write to make this happen. It's a lot more involved than that. It looks like this basically. So we need to do various inserts and pull out the old data to put new data in. And what you actually end up is inserting another 2 rectangles. So there's this idea of splitting, and it basically says that you need to make sure that your timestamps don't overlap, but also that you can't model like an arbitrary polygon. So you have to split at some level and create duplicate rows that allow you to then to fill in the temporal coordinates. So this is what's going on here. So again, all that SQL just to effectively do this splitting operation. It's essential though for the model to work. Again, if you want to do something like delete, here we say he sells the flat. We don't know who buys it. Let's just say Peter sells it. So you can see there's like this gap in the top right hand corner there, where the information of Peter is no longer valid. And again, you sort of have the SQL to insert and update into the table. And then there's some more information learned about this particular flat. So we found out that actually Eva purchased it earlier than we found. Maybe she picked up the phone and explained the situation, or some new records came to light, or someone made a mistake when doing the initial data entry. And now we have this new version, which starts on the 3rd of January, and you can see on the diagram on the left that on the right hand side of the diagram, the bottom of the Eva section goes down as a dip now. And this is again representing the change. But behind the scenes, you can see we again have to split the rectangles and insert rows to account for this shape, which is now forming of the region of validity for that version. And this is the SQL to do that. And there is a sort of point in the book that you can technically split in different directions. So this is something to be mindful of if you're ever implementing this algorithm. And then we find out maybe that the what we just learned about that correction wasn't actually quite true, and it wasn't the third, it was actually the fifth. So, you know, while she was telling us that we'd made a mistake, you know, we made a mistake again on top of that. And so this is the reality of many of these sorts of systems, is that there's always exceptions and edge cases, and we need to be able to capture that complexity, but without losing the information that's already been entered into the system. So here we're deleting, and it's again changing the shape. Here's some more SQL to show you how to do that. And then we may find out that Peter actually purchased the flat on the 12th. So again, we're updating the table. This is the idealized version. If you actually want to implement the SQL, this is what it looks like. It's just an endless updates to these rectangles. And this is essentially the heart of the bitemporal problem. Anyone that's solved a bitemporal problem will have immediately recognized the complexity in this SQL. And whether you do this in SQL purely or in your application code or in your ORM, it has to be modeled somewhere. So this is the nearly the final result of this diagram here. So that's just inserting information. I haven't told you anything about querying the information, of course. And so the next section in the book talks about queries. And there are basically three types of queries that are generally interesting. One is to give you, using the stable basis concept, we were saying the basis is the 18th of January. What was the history as best known as of the 18th of January? You know, what was the ownership of the flat? And if we cut the diagram down the middle, and then sort of trace it from the bottom upwards, we see the history evolving. So Eva owned it from the 10th until the 15th, and Peter owned it from the 15th onwards indefinitely, as of the 18th of January. Of course, if you were to slide that line just slightly more to the right, then you'd see that Peter no longer owns it. But we can take this time slice cut through the history. Similarly, we can do a horizontal cut, and this one actually shows here all the different rectangles it has to intersect. And what this is giving us is the history of corrections at a given point in time. So on the 13th of January, the ownership changed twice, but we see there are sort of three rectangles that intersects, 1, 2, and 8. So this is a valid time slice. And then probably the most general query that people actually want to do on these sorts of data models is point in time, where we're essentially saying we're going to lock the transaction time here, or system time, and valid time, and just look at the value under the point. And we want that to be fast because, you know, we're building an online application which has lots of users and a lot of concurrency and complex queries. And so generally speaking, the as of now query is what most people want. And when you're normally thinking about databases that operate in now, this is what's happening. Yeah, we're just looking at what the value is under the intersection of those two lines. So you may have heard of like an as of query. Well, there's sort of another word you could use, as of 18, as at 13, valid time equals 13. And so yeah, this is the language and the way we think about querying in a traditional sense. So just to summarize what we just discussed, there are 2, 3, or 4 timestamps, or you can have various ways of storing the data in your tables. You must make sure you don't have overlapping keys. There are performance considerations, of course, especially when you're adding all these extra steps in order to insert data and then to query it back out again. I've said 4 timestamps is best. We'll talk about SQL 2011 again in a minute. But yeah, there's always trade-offs if you're implementing this yourself. But you may notice some of the difference in queries if you don't have the if you have 4 timestamps, your queries get simpler because it's less binary operators to compare things. So that's basically a summary of the ad hoc approach to bitemporality. If you were to cast your mind back to 1999 and don't use any of the other database features that exist, that is an ad hoc implementation. People may write that on a project, but they will also think, well, how am I splitting up my data schema to make sure I'm not duplicating too much data as different versions change? You know, should I have smaller tables, with fewer columns? Understanding what you do about duplicate primary keys is important. Knowing which indexes to put on which columns is also important. Being able to test that rigorously, make sure it works, and it's going to give you consistent low latency in production. And then just generally like making sure that your code is accurate and is correct, but that it's also scalable. It's just very hard to do right. So what we've seen is that projects that do this on project time inevitably end up with a lot more code complexity than they bargained for, because it's a hard problem to get right. Here's a list of different trade-off dimensions. So for instance, yeah, I've already said about read latency versus write latency, but maybe you're deciding whether or not you even want to do bitemporality at all. Like there is just a cost. There is some overhead in any system to storing history. Mutation is generally faster. So deciding whether you want to make everything in your database bitemporal, it's worth thinking about these things. You know, what is the cost of storing information indefinitely in these huge history tables? What granularity do you need? Do you need to have some retention or roll-ups or anything like that? Do you want to make queries easy to write or easy to read? Like there's some trade-off there, I think, as well. And ultimately, you know, what is your budget to deliver a project? Because if you don't have a grasp of this going into a bitemporal project, you know, it's very difficult to predict what the likely outcome is going to be. So, of course, re-engineering things is much harder than getting it right first time. So yeah, unfortunately, there's no easy answers, as we'll come on to find out. So SQL 2011, I've mentioned this, so dropped the name a couple of times. This is ISO approved standard. Various databases collaborated to implement it and to agree the standard, ratify it. So in particular, like Oracle and DB2, and maybe some of the other databases to the last years. And the key thing about SQL 2011 is basically just temporal functionality. There's not really much else in that spec. So unlike 2016, where there was loads of these JSON operators taking after Postgres JSON B columns, SQL 2011 was really focused on this temporal functionality. But unfortunately, the reality is that not everyone's implemented it properly. And even today, I think there's still demand for it. It's just very hard to implement. So in the wake of the standard being published, there was this paper written, which is very good. It's only 7 pages or so, but it has some examples, breaks down what was in the standard, what those features do, maybe what the gaps or future things that would have been included if this line of work was continued, like how they'd extend the standard further. And the examples it gives is explaining exactly the syntax that you now have. So in this DDL, data definition language, the SQL create table statement, we have the ability to say we're going to create a period for system time. And so this is like a hard-coded name on the database table. So it's like an extra column which stores this period reference called system time, which is actually like a compound of the system start and system end. And then we also have e period slightly further up, which is valid time basically. So it's user defined. Of course, here it means employee period. And you can see again this without overlaps concept is very important, and you have to remember to define that on the table. And so you can actually mix and match these things. You don't have to have valid time and system time. You can just use system time by itself and get some value, but really the beauty is in the combination of both. So, and then you have the with system versioning at the end. But anyway, the point is you don't get this for free when you start using DB2 or SQL Server or the other databases. You have to think about this in advance. You have to think, which tables am I using? So the other things that are added in the standard, we have this update for portion of syntax, which basically allows us to avoid having to write that sprawl of SQL just to update these rectangles. And we can see here we can bisect, we can cut the range of validity from the 1st of January to the 12th of November the next year. We can cut that in half and insert something in the middle, and that's quite a powerful thing to do in a very short amount of characters, whilst also knowing that there's system time being preserved as well. It also gives us expressive querying, so we can say what was the department where the employee worked as of December the 1st and recorded in the 1st of July 2011, and it gives us this syntax for system time as of, and then we can use this word contains. The contains is an example of a period predicate. So the other ones it ships with, or the standard promotes or standardizes, it succeeds, precedes, immediately succeeds, immediately precedes, and overlaps. And you may recognize these diagrams as like Allen interval algebra, which is essentially a way of creating temporal logic for like complex periods. So there are even more things that can be done in this space, and we'll perhaps talk about this in the Q&A at the end. But certainly it's a lot quicker to write this than all the less than and greater than you'd need to do otherwise. So given this capability in SQL 2011, the point in time query we looked at earlier, give the owner of the flat as of 13th, as of the 18th, as at the 13th. We now have this language for system time as of and contains. And so if we just write our queries with this, that will give us the point in time now query without having to have more complex queries than necessary. And this is quite a good default in the standard, but arguably it's perhaps not as simple as it could be. And wouldn't it be nice if it could assume that you always want a point in time query unless you want otherwise? And that's something we're keen to explore and talk about. And when the standard was released, there was a lot of hype. This is a video by Craig Baumonk, who sadly no longer with us, but he was quite passionate at that point that this was going to revolutionize a lot of legacy financial institutions who really needed to get their act together in the wake of the global financial crisis and make sure that they're recording data more accurately. And so he was a big passionate advocate for bitemporal data management. And he outlines some of the risks and pitfalls in those industries quite well. But unfortunately, we're 12 years on from that, and nothing's really changed. Like this webinar is an example of trying to popularize this idea, because I think it lacks understanding and awareness. So you might wonder why isn't it commonplace? Well, I think the short answer is it's very hard to retrofit this onto existing database architectures, and databases have existed for a long time. Being very happy with just tracking now, and now you want to impose these extra conditions that they have to not only store lots of data, which means much bigger tables for a lot longer, but also then have these very complex queries and intersections that impact all kinds of previously solved problems like join planning, and how primary keys should be dealt with. And in general, people prefer to separate this these more analytical heavy use cases from online application building. The OLAP and the OLTP are separate in a lot of instances, but if your online transactional system database isn't keeping the history itself, then you have to be really sure that your change data capture is working well. And really, SQL 2011 sort of straddles these two worlds, and it says, well, let's just build applications assuming that we can store the history. And it just doesn't work with the databases as they've predominantly been used over the past. And then, of course, for developers, if you're not aware that bitemporality is a thing, it's not being used by default in your database. You have to be sure that your database has this feature, and you have to understand how to use it. And then, of course, the performance implications aren't necessarily obvious if the query engine was written 20 years ago, and doesn't make it easy for you to tune or tweak the performance for your use case that you have. Here's a blog post written by Paul Youngworth a few years ago, looking at the state of the SQL 2011 specification as it was. So he reviewed the bibliography. Interesting point there about schema change, and I think this is something the standard misses a little bit. But schema and bitemporality are quite complex. Yeah, they're quite hard to think about together. So you either have to sort of copy your history tables to add extra columns, or you have to track the schema in a temporal way itself, which is something, again, that the standard doesn't really address. So arguably, there's some gap in the standard, which makes using the functionality kind of difficult if you have to think about how to remove the constraints to change the tables and then put the constraints back on. And then a couple of years later, he reviewed the adoption of these features across the different databases. So here he's looking at SQL Server, MariaDB, Oracle, DB2, Now, since this analysis, MariaDB has added temporal tables, so they're an example of a database which, in theory, you can pick up and run with right away. I haven't personally used it, so I can't vouch for it, but there's a good presentation on the topic in MariaDB. Other databases like MarkLogic have discussed bitemporality in the past, and I think regardless of what technology you use, I think we should be pushing our vendors and in the upstream to offer this functionality. Otherwise, it will never become used and adopted. Teradata again is another big player in the database space who's really explored this at one point or other. They actually collaborated with Richard Snodgrass on this case study, using their SQL support, which actually predates the SQL 2011 standard. So they were ahead of the curve in a sense. And of course, the question on everyone's mind is, what about Postgres? And unfortunately, Postgres just hasn't moved. Paul, the previous blog I showed, he does talk about this, but Postgres just hasn't had the critical mass of core developer interest to implement anything in the core. There is this user at the top, Hetty. She's been working on the Bitemporal library for I think the past like 7 or 8 years, which does add some function using GIST indexes, the spatial indexes for bitemporality, which allow you to have reasonably good performance with Postgres, but it's all in user space, so it's not a normal extension. And I haven't sort of tested her extension, but she seems like she knows what she's doing, and she's been working on it for a very long time. So I think that's probably the state of the art in terms of bitemporality in Postgres. But if you do just want system time only, then there are a couple of extensions for that, which are probably worth checking out. And a final question I'll cover, artificial question. I'm assuming you're asking yourself is this diagram looks cool. If I have a bitemporal problem, I'm probably going to need something like this in order to understand what's going on. How can I generate things that look like this? And I couldn't find a good answer for that, so I ended up building a tool myself called the Bitemporal Visualizer. If you Google that, you should find it fairly quickly. But it essentially allows you to copy paste some output from like your Postgres PC call output and dump it into a text area, and then it illustrates it and allows you to reason about the different versions at different points in time. Basically, all of this is a journey that I'm on, we're on, and I think everyone else is on as well. So as we learn more about bitemporality, we'll tell you more. But this is about everything I know about it, and I'll be happy to answer any questions. Now, thank you.
Thank you very much, Jeremy. Just a reminder, if you do have any questions for this, please do pop them in the questions box, and we'll keep an eye on that and answer them as we go. We do have a few questions through the course of the webinar. Thank you to the folks for submitting those. So we'll start off with Jake, and this is a question from around about slide 61. I think I didn't spot the exact slide. But in some of the examples, infinity is modeled as a very large date. So in this case, it's year 9999. And in some domains, you might want to model far further than that to the future. So thinking about sort of in a game, for example, in a very futuristic game. So does XT have a principled model of infinity, or does it also use that same kind of max date style valid too?
So I think you're best to answer that one, James. Yeah.
Yeah, I'm happy to. So yes, we do take a principled model of infinity, and in this way we take inspiration from Postgres, which allows null on either end of the interval, which means unbounded. And I think in a previous life before XT, there was such a time, believe it or not. In a previous life, I've definitely seen cases where we've had to work with, for example, MySQL's zero date, meaning start of time. And I'm sure we've all seen sort of user-facing UIs where those kinds of dates have leaked out. So yeah, it's definitely something that we'd like to, an area of complexity that we'd like to take away from the user as a bitemporal database. Cool. I should say as well, we do know that we're almost out of time, so we'll stay on here to answer your questions. But if you do need to drop off, you'll be able to see the full Q&A in the on-demand recording when we release it next week. I've got another question from Tim. I think this is around about slide 68 or so. So love that you're covering the historical context, Jeremy, and precedents for sort of bitemporality. So particularly looking at Snodgrass's research. Actually, there was a slide before 57 that showed the terms used by various systems, including Kafka. And I wonder if you can compare and contrast how the main modern systems handle bitemporality, and especially interested in XDDB and Atomic.
Yeah. So if I go back to this thing, right? So I don't think anything's really changed since Paul did a review here. So if you're using, these 4 databases are, definitely in the top 10 of popular databases. Their state of the art isn't bad, but there are definitely caveats to how you use these features. So I think it requires a lot of thought or forethought to think, yeah, this is the right time to use this database feature. Of course, if your database doesn't support any notion of system time or valid time, then you're going to end up implementing this in user space, which is doable, right? I showed you in this presentation that it's not infinite amounts of logic, but it is something you need to make sure you get right and budget for. In XT, we've really gone to town on making bitemporality as easy to think about as possible. So yeah, XDDB, which has been going for, as I said, almost 5 years, and from day one, it's always been a case of putting in documents, and when you pull out the document, you can see the different timestamps. But you don't really have to think about it until you actually need to use it. Whereas a lot of these other systems force you to consider the schema, and as you do select star, you see a lot of information which you don't necessarily care about, and the impact on primary keys and things is more profound because of the way they treat schema and schema change. So yeah, I don't see mainstream technologies really solving this very well, which I think is part chicken and egg problem. That means people don't really use it, which means they don't bother. The vendors don't bother to invest more energy in making it better. Yeah, I won't comment on Datomic more than just to say I don't think it really has any way of fabricating valid time beyond what we sort of discussed, where you have to track the versions and pull out versions into separate entities. Thank you, James. Was there another question?
Guess who forgot to click the unmute button? Apologies for that. I'd add on that sort of broadly speaking, so we do follow the semantics of SQL 2011, and this is largely so that we maintain compatibility with other tools and things and databases that do support this to their various degrees. But there's one area in particular where we've made a really conscious decision to deviate from the spec, and that is in the area of valid time. So in the spec, the default is that queries and transactions both apply for all valid time. And so we, as Jeremy said, we prefer that the database behaves as closely as possible to a traditional update in place database. So we in fact default to transactions defaulting of as of now. So when you put in an update, it defaults to as of now to end of time. And what this does, this essentially means that you keep all of your existing atemporal queries as they are, but then you can incrementally add bitemporal queries as you need them. And I think a little bit of the context of SQL 2011 is I think that I get the feeling that they were really trying to keep as much backwards compatibility as possible. So very, very much sort of going along the idea that we need to make everything still look like a table. And I think it's quite we're quite fortunate in the respect that we can deviate from that a little bit. Cool. So next question, I'm going to keep heading on through. So this is from Jake. He's asking how would a constraint like unique work? Does the data have to be unique over all time, or just at the time of writing? And would changing historical data violate that newly added constraint? So I would say there's a it seems broadly speaking that the pattern for SQL 2011 bitemporal tables is to change the unique constraint ever so slightly. And the unique constraint then becomes it then becomes your existing primary key and then your valid time period without or what's called without overlaps, which is a new SQL 2011 construct. I think it may have been on Jeremy's slide, unfortunately. Slide 88 potentially. Let's have a look. That's the one. So you'll see here primary key of the employee number and then e period without overlaps. And what that does is that says that for any system time, you can't have any data that overlaps in the valid time period. Okay, let's have a look at the questions. We've got one from Andreas. Does XDB provide any support for schema revolution?
Well, I'll take that one because you've been talking for a while. Thanks, James. So XDB at its core is schema-less, so it doesn't assume any knowledge of column types or what columns exist. It tracks these things incrementally so that you don't really have to tell it in advance how you're going to use it. Of course, there's a trade-off here, which means you still have to model the schema somewhere. And over in the coming months or so, we'd like to add more schema full features to be able to sort of lock down what you can or can't put into the table. But at its core, it's schemaless, which means that it sort of avoids or bypasses the problem of trying to marry bitemporality with the standard SQL schema model because there is no schema, so it's convenient in that sense. But yeah, obviously your application will have a schema at some point, and that needs to live somewhere. But we view the idea of having a schemaless core as quite important to building a system in layers, so that you build a schema layer on top. And at that point, we'll have a more sort of reasoned or passionate view about what a temporal schema looks like, or a temporal model of schema. And feel free to add to that, James.
No, good for me. Thank you, Jeremy. Okay, I think that's about it for the questions that we've got at this time. So, Jeremy, I suggest we move on to the XDB demo. So, for everyone on the call, this is the formal end of the webinar, if you like. But we'd invite you to stay on for another 10 minutes or so to see XT in action. And of course, if we've got more questions at the end of that on either bitemporality in theory or XDB in practice, then we're happy to take those too.
Cool. Oh, wrong screen. Okay. All right. So we're viewing a Linux machine. So if the connection drops, it's because VNC broke. Yeah, let's see what happens. May the demo gods be with us. So if anyone's not looked at this link already, on xtdb.com/v2, we have this early access page which describes the upcoming major release of XT, which we're working on at the moment. Of course, we hope it to be generally available at some point, within the next year. But currently, we haven't released an alpha officially yet. We're just looking for people to give us early feedback on the way it works. But yeah, XDB2 has been designed really with the SQL 2011 specification in mind. We wanted to make sure that we could solve the problem of how to handle the query language and all the ways you might want to extend or adapt that to be even easier to use and give you the performance that you might need as well. So in version 2, we have this nice clean model of being able to use it just using a Docker container, pointing at object storage and a log of some kind like Kafka. And you can run it up in AWS or GCP as hopefully a push button. You can bring it online very easily. In this example, we're going to use a Docker container. So I've actually already pulled a Docker container, and I can just run the container here. It's going to take a few seconds to start. While that happens, I'm going to explain what else these instructions show on the screen. So XTDB is written in Clojure, which is a language that Juxt is primarily expert in. Clojure is a Lisp that runs on the JVM. So it is a JVM database currently. It's a language we're very comfortable and familiar with. But you really don't have to think about it in order to use XT, or you shouldn't do. So the idea is that by using SQL, we can put this behind a nice cloud API and offer this up as a service potentially, and have people use it who have no idea what Clojure is and don't need to. So we can see here that our node has started. So we've installed it as such. We've exposed a port on 5432, which is like a Postgres common client port. And then we can use a tool like pSQL to connect to it. So pSQL-H localhost will open a connection to XTDB. So now we're in a session which is compatible with the Postgres wire protocol. We're not necessarily saying this is always the best way to use XT, but this works for now. So you can use familiar looking SQL, standards compliant SQL. It's been tested using the SQLite test suites to check conformance of all the logic and grammar. You'll note we have an XT ID column, so we use a global ID in XT, which means that every table has a single ID column, and this allows us to be schemaless, so you don't have to say which columns are the primary keys in advance, but it also gives us a stable identity to track over time. So if we insert into the post table, we've never declared posts. This is a brand new database. We haven't said there's a post table, but just by inserting into posts, we're actually essentially creating a post table with a couple of columns that we've just defined by copy and pasting. So user ID and text are brand new columns. It's returning 0, but it has inserted a row, as we'll see by selecting post.text from posts, and we'll see that we have one row. So this is the schemaless promise of XT coming to life. This isn't necessarily related to Bitemporality, but I'll show you anyway, because it's interesting, because in order to be schemaless, you want to sort of embrace that. JSON-B in Postgres has really shown that everyone does want to be able to denormalize data and store it in a way that other systems can understand. Rather than using JSON here, we're actually just inserting these nested SQL records, so structs and objects, which approximate JSON. It gives you the same power and flexibility as JSON. And so we can query this nested data out from within our rows. So within this, so I should have added, we're now setting to people table, and so within the friends column we have this nested value, so it's an array with 2 objects. And here we're querying the second object, and of course SQL is 1 indexed, so that is Kath. So that's why we get the answer we do. And of course XT is natively bitemporal. So if I run this query to do a select star, we're going to pull out all the rows that we know about from people. So we run this, we're going to get a bit of a mess, which I can try and zoom out on to make it slightly easier to read. But you can see we've got these built-in columns. So XT is automatically maintaining valid from, valid to, system from, system to, just as we were discussing in the presentation. And of course, those timestamps match, right? So the valid from and the system from are exactly the same, because we haven't overridden the time which we're pushing the data into the database. So they use the same timestamp. And now we can do things like put data in into the future. So here we're or into the past. So here we're inserting into the valid from field in 2019. We're inserting 2024, and we're also going to insert in 2025. So if I copy and paste this, all right. So we've updated the post table. If we do a select star from posts again, right. So by default we will see everything that's valid, and you may notice up here we can set it to as of now. So by default, XT follows a 2011 specification of viewing all versions, but we think it's a nicer experience to just show what is currently visible to valid time. So this is again sort of constraining the point we're querying on the temporal diagram to a single point in time of valid time and system time. So yeah, here we're seeing two versions. We're seeing the one we originally inserted back at the top of this instructions, hello world, and then we're also seeing 2019 because of course we've inserted it into the past, so it's still valid, and you know, until someone says otherwise, that thing is valid. So it's in our table. But we can now look at this table as of a certain date, and so we can go into the future and say what will this table look like in 2025. And we can see here that we have an edited post, which appears later. Cool. So and then we can do something like this, where we're using the new overlaps SQL 2011 period predicate to say show me all the edits that overlap each other, basically, for this post. So it's a post where the edits overlap, and it gives us 3 results, which is correct. So yeah, notably absence is the new happy to 2024, but yeah, maybe I'll let you understand why that is as an exercise for the reader. And then it's also worth mentioning that in XT we have this idea of being built in Apache Arrow. So Apache Arrow is this columnar memory format for doing data processing. It's used a lot in machine learning and data science toolkits, and other databases are embracing it as well. And we think it's a very good sort of standard to be working with. So we have this ability to query some data that's out on a public Arrow file over here. This one says we love strangely, of course, which is when we first launched this example last year. And then we have this ability to erase information. So of course, something I haven't really mentioned at all in this talk so far is what happens when you do want to actually delete something for GDPR reasons. You still need some semantic or way for the query language to allow you to do that. And so we have, this isn't in the SQL 2011 standard, we've added this concept of arrays, which overrides the constraints of the table to make sure that that happens. And then if we query our people again, we just, I think we can just do select star from people. Okay, I'll need to do that. Well, I can do the XT ID from people. Oh, sorry, people. There we go. So yeah, so it's erased it from the example table. All right, so that's basically the end of this little demo, just showing off some of the temporal query functionality that exists in XT today. We're going to keep working on this. We think it's an exciting area and want to make the indexes that support it as fast as possible for supporting the as of now use case, because we think that's important. And XT version 1 has always been very good at this as of now use case, but version 1 lacks the ability to do analysis like across tables. I didn't even have the concept of tables, but across large sets of history, whereas the new engine has a more first-class way to internally work with these bitemporal relations. So that's a little demo of XT. Thank you for watching, and I think I mentioned already, but I'd give this a read as well because it's open on my screen. But yeah, that's everything.
Thank you very much, Jeremy. So I just got one further question, which is from Tim, who didn't realize that XT can look like a SQL database. Just figured it provided an even-centric view of data like Datomic. So does this mean that a closure app can use a more Datomic-like API, and other apps can just query with SQL, so the system doesn't have to be all closure? Yes, absolutely. And this is exactly one of the things that we wanted to do with version 2. So all of this data that Jeremy's been inserting here is queryable both from SQL and from a XT1 Datomic-like Datalog API. So for example, you can insert data in SQL and then query it in Datalog, and vice versa, insert data in Datalog and query it in SQL. And this is one thing we were particularly aiming for, because we're quite conscious that certainly in some companies that we've been working in, while you might get the developers who are absolutely sort of absolutely bought into to Datalog and the productivity gains that it brings. We're also very pragmatic to know that there's one hell of an ecosystem behind SQL, and so well, an ecosystem, but also a wealth of sort of decades of people's experience. So this is definitely something that we were targeting. Yeah. All right. A question from Zachary: how does it do with graph clique? Jeremy, I know that's up your street.
Yeah. So one of the things that I was quite enamored with version 1 of XT is the ability to lazily query a graph of data. So because XT is schemaless, you can treat things as if they're all joinable. So you can have like a massive table and do these arbitrary joins within the table. And in version 1, we have a sort of a one-trick pony in the query engine, which allows you to lazily join across a number of dimensions. So you can do a graph query and walk the graph in a way that doesn't consume enormous amounts of memory. And so that's very good at doing graph analysis workloads. So wherever you have like the word clique, a graph clique or like a 5 clique or something is a geometric description of a shape of data that says like maybe these 5 things are connected or all connected to each other, and it's useful for doing things like fraud analysis. You want to say which bank accounts are all passing money between each other to sort of disguise what's actually happening in real terms. So being able to efficiently execute that as a high-level data log query was quite a nice capability in version 1. In version 2, we've not built that algorithm again, so that would be work to do in the future to reinstate that capability. So we do have some users who make use of that, but broadly, it's like, it's nice to have, but people aren't necessarily going to town running these giant graph analysis queries. And again, Bitemporality is a big important pillar for XT in a way that graph analytics perhaps aren't.
Excellent, thanks, Jeremy. Okay, that's all the questions we have on the chat at least. So just like a big thanks to everyone for joining, and a big thanks to Jeremy, of course, for giving us a tour of Bitemporality and a tour of XT. So as Adi says at the start, we will be sending, I think, well, GoToWebinar will be sending out the video at some point next week. So please do look out for that, and feel free to share it to folks who didn't manage to make it today. If you do have any other questions, please do get in touch with us. So we hang out in a few different places. One of which is discuss.xtdb.com, which is the XTDB support forum. And if you want to email us, you can email us at hello@xtdb.com. Okay, I think that's all from us. As I say, thanks again for joining, and we'll hopefully see you next time.
Thanks. See you soon.